Okay, so at this point we want to show that this Catalan formula actually holds, and in order to do that we're going to be doing a proof by induction. So I'm going to be doing the proof here by induction, like I said, and I'll let you try the base case on your own. So testing the base case when k is equal to 2, we end up with a true statement. So our value 2 matches what we had found earlier when we used the formula that was given. Okay, so base case is basically finished, and now we have to do the inductive hypothesis. So let me go ahead and start with the inductive hypothesis. Okay, so inductive hypothesis, we suppose that the formula actually is true. We want to show that it's true for the next integer k plus 1. So, or in other terms, we want to show that it's true for cn plus 1. So let's find out what we get when we plug in n plus 1 into the formula. So 4 times n plus 1 minus 2 divided by n plus 1 plus 1, and then cn plus 1 minus 1. This turns out to be 4n plus 2 divided by n plus 2 times cn, but keep in mind that cn itself, we can use the recurrence relation from the first page, or rather the definition from the first page, to get the answer to this one. So it's going to be basically 4n plus 2 divided by n plus 2 and multiplied by 1 over n plus 1, because that's what cn is, times 2n choose n. Okay, let's break it down even more so that we can get a clearer formula. So we want to show that cn plus 1 is actually 4n plus 2 divided by n plus 2 times n plus 1 times, when we break the 2n factorial, 2n divided by n, well, 2n choose n, when we break it down we end up with 2n factorial divided by n factorial, and then n factorial one more time. So this is what our goal is, basically. Okay, another way of saying this goal is to say something like this. It's 4n plus 2 times 2n factorial, all divided by, if we put these three together, that's the same thing as saying n plus 2 factorial and then n factorial. So that may be a little bit easier to get to, so that's why I'm rewriting it 3 more times. So here we go. Let's go ahead and start it off at this point by saying we know from the first page, we know that cn is actually equal to 1 over n plus 1 times 2n choose n. So cn plus 1 will be 1 over n plus 1 plus 1 times 2n plus 1 choose n plus 1, which translates to 1 over n plus 2, and then 2n plus 2 choose n plus 1. Okay, so this whole thing then gives us cn plus 1 is equal to 1 over n plus 2 times 2n plus 2 factorial divided by n plus 1 factorial times, if you subtract 2n plus 2 minus n plus 1, you get n plus 1 one more time factorial. Perfect. Okay, so using the properties of factorial, I can break some things apart. So the 2n plus 2 can break down to 2n plus 2 times the previous one times the previous one factorial, and then same thing with the n plus 1 factorial and n plus 1 factorial. So at this point, I'm going to try to rewrite the expression one more time by factoring the 2 out of this term. So it's at 2n plus 2, we can factor the 2 out, and if we did that, here's what we end up with. Okay, so, and at this point we can reduce some of the terms. So basically there aren't a whole lot of things we can reduce, but we can reduce at least the n plus 1 with the n plus 1 there, and that's pretty much what it's going to be. So at this point, here's what I'm going to do. I'm going to take the 2 and give it to the 2n and to the 1. Then I'm going to put the n plus 2 together with the n plus 1 together with the n into one term with the factorial. Okay, so let's do that. So there you go. Once you put all the factorials together on the bottom and you rewrite it, you end up with this expression, which is exactly what our goal was in the comment that we made. So that's pretty much it. So this is the end QED. Perfect.